Okay, let's get back to our lesson. And now I know there are many technical issues involved with this blackboard, and part of it is my fault because in the random block, for the same issue, there is the multiple answer, there's the calculated formula, and somehow for the multiple answer, there was a question, what must be? But then for the calculated formula in copying and paste, somehow I forgot that. And not being so young, it happened. So for those, all of you, when it involves that calculated formula where no question was asked, it will just simply be discounted. All right, so that you are not punished. And so instead of 150, everybody is now out of 140 because that one. But for the part where there was a multiple answer, then you should and be able to answer that question. So that will not be. And then for the other one involving permittivity equal to 0, I'm sorry, but for the one where the permittivity is 0, that I am absolutely shocked. But so you will not be penalized for that. Okay. So I just wanted to, it will all part of this random block where it's the same question, but either as a multiple answer where you have a choice or calculated formula, basically to see whether you got the right formula before you got the answer numerically. But anyway, I'm sorry, this particular Blackboard exam has been a stressful one for you and a stressful one for moi aussi. Yes, I have to now go with a grader and explain, and then I have to decide what to do. But anyway, you will not be penalized for these technical issues. Okay? Any
So,
comments or questions?
Professor,
Yes.
for the permittivity of where it was zero, so the answer should be zero for everything, right? So I just put zero for the voltage and even for the electric field because
Yeah.
permittivity
I
is
mean,
zero. And
it should not have been permittivity should not have been zero. The fact that
Mhm.
it ended up zero was something having to do with this way the random block worked, and so you will not be penalized. That's all I'm trying to say. So
Okay,
do
sure.
not be stressed out and say, ooh, I should have done this, I should have done that. It's not your fault, it's random block. And in case of the other one, it's my fault. Okay? You will not be penalized. So what matters is how you do on the other questions relative between the average and what you did. But you will get partial credit for these questions where you gave an answer in scientific notation where it did not ask you for it, but you gave it in scientific notation. I will tell the grader to actually give you correct if it is the same, except that it is in scientific notation instead of what Blackboard says. Oh, it should be in uh, zero decimal place, something like that. Okay, can we now go on? All right. Now, I just wanted to sort of finish up on chapter 21. By the way, homework 21 should be up and it should be due October 15th or something like that because we have been covering magnetic field. And I want to now end this magnetic field. Wait, where is it now? Oh, did I start the recording? Yes. Yeah. I want to end the magnetic field one where we already learned about the coil, that if there's a coil with a current going around the coil, it will produce a magnetic field. And remember the right hand rule number 2, which says that if you point your thumb in the direction of the current, then there will be a magnetic field wrapped around your thumb. Well, if I now have a coil, if I have a coil where this one is coming up and going in, coming up and going in, then that means that now I have my thumb going in the direction of the current. There will then be a magnetic field underneath it, and it will be in this direction. And what now people are able to do is to make a solenoid out of it. Namely, you now have a coil, not a single coil, but you have now 10 turns of this current. And if you turn this thing with one, you get a magnetic field of mu 0 I over 2 pi r. But if you now have 15, then the current is now bigger, because what you have done is you have now made the second coil have its magnetic field, third coil has its magnetic field, and they are adding up because they are all in the same direction. So you are now increasing the magnetic field through this thing that we now call solenoid, and the engineers have figured it out that you can re-express it in terms of the number of turns per unit length, and when you do it that way, the formula turns out to be this. The engineers have figured out, because this is a circumference of the circle and you now have so many circles, so it is now this formula. And the people who use solenoid, they know, according to their design, that they have so many turns per length, per unit length, and the current they send through it by the whatever's the battery, by whatever's the source, then the magnetic field of this solenoid now will be strong, because my N is up to me, I is whatever's my source. Okay, now I want to end this chapter with a very important law called Ampere's law, Ampere's law. It is sort of like Gauss' law. You remember early on for the electric field, we had the Gauss law formulated by this mathematician, physicist. Well, here is now a version of that Gauss law for magnetic field. And this Gauss law just says, you tell me what is the current that is flowing. Then I will now mathematically draw let's say a contour. They call it a contour, right? And then they say the actual net integral, or the sum of the parallel component of the magnetic field along your circuit, along this contour, that if you now just simply add them all up, that is dependent only on what is the current that is flowing through. And for the people who are familiar with calculus, this is the nice formula for saying that it is the circuit integral. Well, just use that language. The circuit integral of the magnetic field in the direction of the circuit, dl. And when you do the circuit, it then only depends on the toy inside the circuit. Somebody had a question? Did somebody have a question?
No, Professor.
And yeah, you had a question? Oh, okay. So this is a useful tool. In fact, you can use this now to figure out the original. This is our Monsieur Professor André-Marie Ampere, who is a mathematician, and he actually did a lot in the invention of the solenoid. And one thing I remember somebody taught me, autodidact was what? Do you remember what was autodidact? Yeah, whoever is not here with us. It's a self-taught. He learned all of these mathematics and parts of physics by what today we call, I don't know, self-taught. So it's in a way, he's a real genius. And when he invented all the solenoid and electric, classical electromagnetism, he was invited by Napoleon. He was invited by Napoleon to come to the French Academy of Sciences and present his presentation, and they have given him a very important professorship. But anyway, and then his name is one of the 72 names inscribed in Eiffel Tower. But now you apply this Ampere's law to the original. Original is, I have a wire that has a current, and this current is I. And then I now take a circuit, a contour, which is exactly a circle. All right. If I take exactly a circle, then we know already from the earlier right-hand rule 2 that if this is a circle of a given radius r, the magnetic field is exactly along the circle. So if the magnetic field is exactly along the circle, then this contour integral, or the sum of the parallel component of the magnetic field with the circuit, since the magnetic field is in the same direction as the circuit itself, then this is just simply B times the actual length of the circuit, and the length of the circuit is, of course, 2 pi r. So then Ampere's law applied to the original right-hand rule, when you have a wire in the current, a wire with a current I, then that tells you right away that B times 2 pi r is mu 0 I, and so you get this. We got that earlier by just simply the right-hand rule, because that's what we were taught. But now Ampere's law is the underlying derivation. Ampere's law is the underlying derivation that says that if you give me a wire that carries a certain current, it will produce a magnetic field which is, according to the right-hand rule, going around this wire, and the actual magnitude of it, oh, it is mu 0 I over the circuit 2 pi r. All right? And so now, just to end, we need also, since we are dealing with magnetic fields, to know the distinction between ordinary materials and these magnets that are what we call permanent magnets. An ordinary material, you can think of it as all these inside molecules. They each have their own little magnetism, but they are random, and the net magnetism is 0. So this is non-magnetic. But a magnetic material, what you call a ferromagnet, what you call a paramagnet, diamagnet, you have now in here, they seem to be more aligned together, so that when you mine it, when you got it out of a a mountain somewhere, when you got it out of the mountain, all this material, they naturally have a certain magnetism. And then this would be what we call a ferromagnet, because they are already all lined up. And that's the language of magnetic material. Now, engineers, they make use of that. I don't even know how they manage it, so we are not going to be concerned about it. Likewise, there is this thing called magnetic levitation. Have you heard of this term, maglev? Trains that are magnetic levitation? Have you heard of it? Nobody's around? I guess you don't know about magnetic levitation. Later on, we will, somebody had that? Yeah. Later on, we will come to this thing called magnetic levitation. And what it is you have the rail has a magnet, and it is, let's say, north this way. And then you, no, the rail has a magnet over here, rail. Then you are riding on it, and you have a magnet also. So there's a magnet on the rail, and there's a magnet in you, and you will have also north. And when you have north, the two magnets, they hate each other. So then you're lifted up. And then what they do very cleverly is, because you're moving, they will now change the orientation of this magnetization in your car, right? In your car, the magnets are due to a very clever arrangement of your electric circuit. And so you will now change from north to south. Now, as you're changing, at first you are you're going this way, and you are being levitated, but this thing is changing, rolling over, and therefore you are propelled forward. It gets a little complicated to figure it out, but that's the maglev industry. And I just wanted to show you this picture because that's important for many high-speed rails these days. Okay, and then the summary is we have the basic Lorentz force, and we have the mass spectrometer, that if you have a charged particle in a given magnetic field, it will go in a circle, and the radius of that circle depends on the velocity and the mass. And we have this re-expression of this, that now I have a wire, and the wire has a current, because QV, it basically becomes the current, related to current. And the force, QV cross B, becomes IL cross B, which is basically a consequence of the original Lorentz force. And we have this Ampere's law that tells us what is the magnetic field, and that is the form of the Ampere's law. And I think I will now quit here. There's no class on Monday because it's a holiday. We will meet again on Wednesday. By then, all the technical issues with the Blackboard grade should have been settled, and I will put up the so-called correct formula on a PowerPoint on Wednesday. So until then, we will have a good rest, okay? Okay, I will stop the recording.